All right, so this is chapter 6. This is about solving systems of differential equations. So we're going to start out with just an introduction. This is going to require a pretty solid knowledge of some linear algebra concepts. So linear algebra is a prerequisite for this course, and I expect you to be familiar with vectors and matrices and how to solve an augmented matrix system, and most importantly, how to find eigenvalues and eigenvectors. So that's going to be really important. If you're not familiar with that stuff, if you've forgotten it, you'll want to familiarize yourself with it again. You need to kind of go over it again and make sure you know how to do that stuff. Okay, I'm going to do a bunch of examples, but you need to kind of have a firm grasp of what these things are, so you'll kind of have an idea of what I'm about to do. So 6.1 is called Introduction to Homogeneous Systems of Differential Equations. And a system of differential equations is just going to be two or more differential equations that have to be solved simultaneously. And usually the different, when you solve a differential equation, you're solving for a function y. Well, here we're going to solve for two functions or three functions, y1, y2, y3. And those functions can be embedded in both equations. So if we see here this example, we've got two differential equations, and both equations involve y1 and y2. So y1 and y2 are functions. So they're like functions of x or functions of t. But there's two different functions. And the first equation says the derivative of the first function is 9 times the first function minus 4 times the second function. And the second equation says the derivative of the second function is 15 times the first function minus 7 times the second function. So if you remember from linear algebra, we can change a system like this into a matrix equation. So I'm going to say that vector y is going to be a vector that contains these two functions, y1 and y2. So those are the two equations that we're trying to solve for. So this vector y will be the solution to our system. So once we find a solution to the system, we'll call it vector y. And so that means that y prime, the vector y prime, is going to be the vector that contains the derivatives of y1 and y2. All right, so that's going to convert this system into a matrix equation. Let me scroll down a little bit. So this matrix equation will say vector y prime is equal to this coefficient matrix. I'm just writing the coefficient matrix for the system, times the vector y. And the vector y is what we're solving for. If we knew vector y, then we would know functions y1 and y2, and then we would know the solution to the system. Okay, so let's say we have this vector y1, not the function y1, but the vector y1. Is this a solution to the system? So to check to see if it's a solution, we're just going to plug it into this equation, right? So I'm going to plug it into, I've already forgot what the system was. Let me go back. 15, negative 4, negative 7. So 15, negative 4, negative 7. I'm going to plug in this vector y. y1s are, it's like we're just guessing here. And we're going to multiply these, and when we multiply them, we should get the derivative of y. And if we do, then we've satisfied this equation. So I'm just going to do this matrix vector multiplication. So I've got 9 times 2 e to the 3t, so that's 18 e to the 3t, minus 4 times 3 e to the 3t, so minus 4, whoops, so that's going to be minus 12 e to the 3t. And the second one, 15 times 2, that's going to be 30. And then negative 7 times 3 is negative 21 e to the 3t. And if I simplify this, I get 18 minus 12 is 6. 30 minus 21 is 9. All right, so that is what we get when we plug in this y into that equation. Now we're going to check, is this vector y prime, y1 prime, we'll say. So is this the derivative of what we plugged in? And it is, right? So if we take the derivative of 2 e to the 3t, because of the chain rule, we have to multiply 3 times 2, get 6. And here we multiply 3 times 3 and get 9. So this works. So this is one of those solutions. All right, I'm going to show you how to get the solutions, but for now we're just going to check to see if we have solutions. You know, how do you check to see if you have a solution? So let's try this one. So you might want to pause the video here and see if you can do this one yourself. So I'm going to plug this in. See if I remember this time. 9, 15, negative 4, negative 7. And I'm going to plug in this vector. And I'm just going to do matrix vector multiplication. So here we got 9 times 2. Negative 4 times 5. 15 times 2. And negative 7 times 5, that's negative 35. And when we simplify, we get negative 2 e to the negative t. We get negative 5 e to the negative t. And if we check that one, this is the derivative of this second vector that we plugged in, right? So that one is also a solution. Okay. So let's check this one. We have 2 solutions, and we're going to check that property of superposition. If you remember that from earlier in the semester, is a linear combination of those 2 vectors also a solution? So I'm adding multiples of these 2 vectors together, and the constants are, we're going to just call it C1 and C2. Those could be anything. And when you add these together, you get this vector. So I'm going to plug this in to my system and see what happens. All right, so I'm going to plug in this whole thing. and see what we get. So I'm gonna, for this first entry, I'm gonna multiply this guy by 9 and this guy by -4 and then simplify. So I'm gonna try to do those at one time. So you'll see what I'm gonna do here. So 9 times 2 is 18. -4 times 3 is -12. That's 18 minus 12. That's going to be 6 C1 e to the 3t. And then 9 times 2 minus 4 times 5. That's going to be 18 minus 20. It's going to be minus 2 e to the, forgot my constant there. -2 C2 e to the -t. 15 times 2 is 30. Minus 7 times 21 is 9. So this is 9 C1 e to the 3t. 15 times 2 minus 7 times 5, that's 30 minus 35, that'd be minus 5 C2 e to the -t. And we're just going to check and see, is that the derivative of what we started with? So if I took the derivative of this, the constants stay outside, and we have to use the chain rule and multiply by 3 here. So it's going to be 6 C1 e to the 3t. Here we're going to multiply by -1, so that happened. This bottom row, multiply by 3. 3 times 3 is 9. And -1 times 5 is -5. So all that works out. So that is also a solution. So this is the derivative of vector y. So that one worked as well. So we see that if we have two solutions, we can take a linear combination, any linear combination of those two solutions, it's also going to be a solution to the system if it's homogeneous. So any linear combination of two vectors is also a solution if those two vectors are already solutions. This is a property of superposition that we learned when we solved second order equations. We're going to check the Wronskian to see if they form a fundamental set. So we're just going to check and see if this determinant is not equal to 0. And all you have to do is put your two solutions in a matrix and find the determinant. You don't have to do the derivatives like we did earlier. We're just going to put the vector functions that we found as solutions, and then we're going to find the determinant. So all we got to do is multiply that diagonal. And when you multiply the e's, you got to add the exponents, right? So that's 3 minus 1, that'd be 2t. And then if I multiply those, I have to subtract minus 6. And again, it's going to be e to the 2t. And we get 4 e to the 2t. Now this guy can never be 0 because remember, exponential functions without adding a constant can never reach 0, right? They have a horizontal asymptote at 0. So these two, these two are solutions. We've verified that they're linearly independent. That means that they form a fundamental set of solutions. They form like a basis for our solution space. All right, so in the previous example, I just gave you the solution of vectors and we plugged them into the differential equation to verify that they were solutions. How do we find those solutions in the first place? Let's examine the solutions more closely. So if I write that solution again, so C1 2 e to the 3t 3e to the 3t plus c2, 2e to the negative t, and then 5e to the negative t. So if you see here in both of these vectors, they have a common factor in the entries, right? So I could factor out these exponentials. So I could say this is C1 e to the 3t times the vector 2, 3. That would be the same thing, right? And do the same thing for the second one. I could factor out e to the negative t. This would be times the vector 2, 5. Let's take a look at this matrix. 9, 15, negative 4, negative 7. I'm just going to multiply this times just the vector 2, 3. Just see what, is there anything special about this matrix and this vector? So if I multiply the matrix times this vector, it's 9 times 2 is 18. Negative 4 times 3 is negative 12. 15 times 2 is 30. Negative 7 times 3 is negative 21. And what I get is the vector 6, 9. And what's special about 2, 3, and 6, 9? This is 3 times the vector 2, 3. And let's do it again with the other one. So I'm going to multiply just by the vector 2, 5. Let's see what we get. So 18 minus 20, 30 minus 35. So that's going to give me negative 2, negative 5. So is that special? Yeah, well, that's just negative, the negative of vector 2, 5. So if you multiply a vector times a matrix and it ends up just being a scalar multiple of that vector, like we could have done the same operation by just multiplying by the scalar 3 and the scalar negative 1, instead of multiplying by this matrix with all these calculations, right? So these are special. If you remember from your linear algebra class, get a different color here, we would say that 2, 3 is what's called an eigenvector. And the eigenvalue, run out of room here, is 3, with eigenvalue 3. And the vector 2, 5 is also an eigenvector with eigenvalue negative 1. So if we were to just, if we didn't know that these were solutions and we wanted to figure out what the solutions were, where we're going to start is we're going to take this coefficient matrix and we're going to find the eigenvalues and we're going to find the eigenvectors, and that's going to tell us everything we need to know to get the solution to the system of equations. Now, when you took linear algebra, you may have thought, I'm never going to see eigenvalues, eigenvectors again, and that's the furthest thing from the truth. These things show up everywhere. these systems of differential equations are real important, and you can solve them with these eigenvectors and eigenvalues. So it's really important and kind of a neat way to get these two classes, linear algebra and differential equations, to kind of merge. So if we were going to start from scratch on this same problem, and I wanted to know what are the solutions to this system, I'm going to start with what's the coefficient matrix? And then I'm going to say, well, what are the eigenvalues? Now we know that it's 3 and -1, but what if we didn't know? We're going to work it out. So we need to find the determinant of A minus lambda I, where I is that identity matrix, right? So A is our coefficient matrix. Minus lambda times I. And if you remember from linear algebra, all that's going to happen here is these are going to change to negative lambdas, and you're just going to be subtracting lambda from this main diagonal. So this is the same thing as the determinant of 9 minus lambda 15, -4, -7 minus lambda. All right, so now we're going to multiply this diagonal. And we're going to subtract the product of this diagonal. So that's -4 times 15. That's going to be 60. So it's -60. So let's change this to +60. So let's go ahead and simplify this a little. So that's going to be -63. It's that one. Minus 9 lambda plus 7 lambda plus lambda squared plus 60. So let's rewrite this. Lambda squared minus 2 lambda minus 3. So that is what we called our characteristic polynomial, right? So we used that in linear algebra. We also used it earlier in this semester, right, when we were doing second order equations. So we're going to set that to 0 and solve it. This guy's going to factor. Those have to be lambdas. It's like I need a -3 and a +1. So I set that to 0. I get 3. Set that to 0. And I get -1. So there are my eigenvalues, and that's exactly what we came up with a second ago. Right. So let's find the eigenvectors. Whoops, can't spell. So we have to do these separately. So I'm going to start with 3. We got 3 and -1, so we just got to do them one at a time. So we need to solve this equation. A minus 3i times vector x equals 0, and this vector, we'll call it vector x1, that's going to be my first eigenvector, okay, when I solve this. So I need to take A and subtract 3 from the main diagonal. The other diagonal is going to stay the same. But here, this was 9. So if we subtract 3, we're going to get 6. This is -7. If we subtract 3, we'll get -10. We have to augment this with 0, right? Because we got 0 on this side. And we're going to have 2 coefficients here. We're going to solve for x1 and x2. That's going to make up our first eigenvector. So let's see if we can figure this out. So let's start by, let's divide this row by 6. Shouldn't write equals there, right? So that'll be 1. -4/6, that's going to be -2/3. And let's divide this one by 15. Get 1, -10/15, that's also -2/3. And now we just subtract the 2 rows. And I get a row of zeros. So remember, I have a leading 1 in this column, and in this column I do not have a leading 1, so that makes that a free variable. So we get x1 is, well, let's write it out completely. I'm skipping a step here. Let's say x1 minus 2/3 x2 is equal to 0. That means x1 is positive 2/3 x2, and x2 is free. It's whatever we want to make it. So let's let x2 be 3, and that's going to cancel out this fraction here. And that's going to give me eigenvector x1, plug it in 3 for x2, and then multiply it times 2/3, I'm going to get 2. So there's that eigenvector that we had a minute ago. Now, could we have picked something different for x2? Yeah, so we could have picked 1 here, and we would have gotten 2/3 and 1 instead of 2 and 3. But you can't pick 0, so the eigenvector cannot be 0. Cannot be a 0 vector. The eigenvalue can be 0. This guy up here can be 0, but the vector that we get can't be the 0 vector. Okay. So that was for lambda equals 3. We need to do the same thing for lambda equals -1. So in this case, we need to plug in -1 for lambda. We're going to solve a plus I, right? The 2 negatives cancel out, times x. We'll call this x2. Set equal to 0 vector. So now we're going to add 1 to the main diagonal. The other diagonal stays the same. This was 9, so it's going to become 10. And this was -7. We add 1, it's going to be -6. Now we just need to row reduce this. So how about, we'll do the same thing. We'll divide by 10. -4/10, that's -2/5. Let's divide this by 15. It's going to make that a 1. -6/15, that's also -2/5 if you divide the top and bottom by 3. And again here, if we subtract the 2 rows, I get this system. All right, so again, we have these coefficients here. This one has a leading 1, this one does not, so this one's free. So x1 is going to be positive 2/5 x2, and x2 is free. So let's let x2 be 5, so it'll cancel out with this 5. And that'll give me eigenvector x2 is going to be 2 and 5. So there is your second eigenvector, right, that goes with this eigenvalue, -1. So once you have the two eigenvectors, you automatically know that eigenvectors are going to be linearly independent. So we don't actually have to check that Wronskian here because we know automatically that these are independent. So the way we're going to write your solutions, you're going to say vector y equals, and you're going to use constants, right, for the general case. You're going to use exponential function raised to the eigenvalue times t, or it could be times x, and then times the eigenvector that goes with that eigenvalue. So it's going to, in this case, it's 2, 3 for the first one. And then C2, the eigenvalue here was -1, so we'll say e to the -t. And then we'll write the eigenvector that goes with that eigenvalue -1. So what do we do about the C's? Well, we need initial condition, right? So what if we have an initial value of 0, 1, 2? So instead of just one y value here, we have two. We have a y1 and a y2 y value, right, for one t value 0. So I'm going to plug in 0 into that solution I just had. So I have C1 e to the 0 times 2, 3 plus C2 e to the 0, right, because 3 times 0 is 0 and -1 times 0 is 0. And then times 2, 5. And I'm going to set this equal to 1, 2. So this is the same as C1 times 2, 3 plus C2 times 2, 5 equals 1, 2. And you can convert that into a system. We'll put these in a matrix, coefficient matrix, and we're going to augment with 1, 2 and row reduce. So this is a good spot to go over how to do this in the calculator if you've forgotten. So I'm just going to, let me make this smaller. I'm going to plug this into the calculator and row reduce it. So I'm going to use the matrix menu. I'm going to edit. This is a 2 by 3. I'm going to put in the entries by row. I'm going to quit to the main menu. I'm going to go back to the matrix menu, go to math, and then I want to scroll up till I get to RREF. And I'm going to put in my matrix A. So we get this system. So let me write this down. I'll just write it down over here. Got 0.25, so I'm just going to call that 1/4. All right. Oh, I messed up there. That is a 1. So we get C1. I'll change that to blue. C1 is 1/4. There we go. And C2 is 1/4. So when we go back to our original equation, we can just plug in these constants. So our solution vector y is C1 e to the 3t times our eigenvector 2, 3 plus c2 e to the negative t times 2, 5. And that will be your particular solution, when you have initial values. So the complicatedness of this is, you have to know how to find eigenvalues and eigenvectors. So I hope this has helped. But it's, once you know how to do that, getting your solution is no big deal. All right, so we're going to do another example. And we have, instead of y1, y2, we just have functions x and y. So here, x is some function of t, and y is some function of t, and we want to know what those functions are. So that will be the solution. So we'll call it solution vector x. And that's going to be the functions x and y. Whoops, I messed up my y there. So that means x prime is going to be the vector that has function x prime and function y prime. So this system, we can write it as vector x prime is equal to coefficient matrix 6, 1, 5, 2 times vector x. So in order to solve this, we have to find the eigenvalues and eigenvectors of this matrix. So let's find the eigenvalues first. So we're going to find the determinant of A minus lambda I, and that just means find the determinant of the matrix you get when you subtract lambda from the main diagonal. It's hard to write and talk at the same time. All right, so we're going to multiply this diagonal. We're going to multiply this diagonal and we're going to subtract it. So 5 times 1 is 5. So we get that. And then we're just going to simplify this. So that's 12 minus 6 lambda minus 2 lambda plus lambda squared minus 5. And then I'll just rewrite that. Negative 6, negative 2 is negative 8. 12 minus 5 is 7. So I want to take this polynomial, set it to 0, and I'm going to solve this. I think this will factor. So these have to be lambdas. Looks like negative 7, negative 1. That's going to multiply to be plus 7 and add to be negative 8. And this is going to give me first eigenvalue is going to be positive 7. This is going to give me second eigenvalue. Whoops. It's going to be positive 1. So those are my eigenvalues. So now I need to find the eigenvectors. So for lambda 1 equals 7, I need to solve this equation. A minus 7i times x equals 0, and this x will be the eigenvector. So let's call it x1 for lambda 1, and that'll be the eigenvector for this eigenvalue. And this guy is just, we're just going to subtract 7 from the main diagonal of A. So A, let's go back up. A is 6152. And we're going to subtract 7 from the main diagonal. And we're going to augment this with 0, the 0 vector. And we're solving for x. We'll call this x1, x2, or you can say A and B or C1, C2, however you want to think about that. We just need some variables here to make up our vector here. Whoops. There we go. All right. So now that's -1. This one's -5. And if you reduce it, you can see this is going to be this and a row of zeros. So this one's free. I'll write it over here. So x1 is 5x2 and x2 is free. So if I let x2 be 1, then I get my first eigenvector. If I let x2 be equal to 1, then this will be 5, 1. So there's my first eigenvector. So let's do this whole thing again for the second eigenvector, or for the second eigenvalue. So we'll say for lambda 2 equals 1, I need to solve this equation. A minus 1 times I times x equals 0, and we'll call this x2 for our second eigenvector. So A is 6, 1, 5, 2, and we're going to subtract 1 from the main diagonal. Augment with 0. And remember, if you think I'm going too fast, just pause the video and go back and watch it again, okay? I'm just going at Aaron speed right now, so if you need me to slow down, just pause the video so you can kind of catch up. So this is going to be 5, 5, 1, 1. And that's going to reduce to this. So again, we got a free variable here. This is a leading 1, this one's not. So x1 is negative x2, and x2 is free. We can let it be anything we want. Let's let it be 1. And we get second eigenvector -1, 1 when we plug that 1 in for x2. So now we have the solution, right? So we can write the solution now. Whoops, we said it was x, right? We used big X for that. Big X vector is going to be C1, because it's going to be general case. E to the 7t, that's our eigenvalue. And then we need the eigenvector that went with 7. So what was that? That was 5, 1. We need the second eigenvalue was 1. So we'll say 1 times t is just t. And then we have second eigenvector. So there is our solution for that vector x. And this solves our system of equations.